In 1886, a scientist studying human genetics realized something that, it must have seemed kind of terrifying at the time.
Oh, definitely. He was looking at family trees and noticed humanity basically appeared to be shrinking toward the average.
Right. Like, unusually tall parents were consistently having shorter kids.
Exactly. And unusually short parents were having taller kids,
It was like every extreme was just getting pulled right back to the middle. And he called this phenomenon regression toward mediocrity.
which is quite a phrase.
It really is. So welcome to today's deep dive. We are exploring a really comprehensive Wikipedia article on a subject that actually grew out of that exact observation linear regression.
Yeah, and I know that probably sounds like a dusty high school math topic that you tried to forget the second you graduated.
Yeah, totally. But consider this, it is literally the hidden engine powering our modern world.
It really is. I mean, it's the invisible architecture behind financial markets, epidemiological research, and maybe most importantly right now, it's the absolute bedrock of modern artificial intelligence.
Right, because when you strip away all the layers of a complex neural network, you often just find linear regression quietly doing the heavy lifting in the background.
Exactly.
So our mission for you today is to demystify this statistical powerhouse. The goal here isn't to force you to memorize formulas or anything like that.
No, definitely not.
It's really to understand how humanity uses math to predict the future and, make sense of incredibly chaotic data. So, okay, let's unpack this, because the idea of just drawing a straight line through a bunch of messy data points, it seems way too simple to be this important.
Well, yeah, that simplicity is kind of an illusion. The most compelling part of linear regression isn't actually the mathematics itself.
Oh.
Yeah, I mean, the math is just a tool. The truly fascinating part is the philosophical assumptions we have to make when we try to draw that straight, orderly line through a deeply messy, unpredictable reality.
We're imposing order on chaos.
Exactly. And that comes with some really profound implications.
So before we can understand how modern AI uses this tool to impose that order, we kind of have to look at why it was invented in the first place.
Right.
Which actually takes us on a journey from looking up at the stars all the way to looking right back at ourselves.
Yeah.
Because long before that geneticist was looking at human heights in the 1880s, astronomers were dealing with a massive data problem.
Yeah, early scientists were essentially drowning in observational data that simply wouldn't line up.
Which makes sense.
Right. I mean, if we connect this to the bigger picture, imagine looking through a 17th century telescope.
Mm-hmm.
Your lenses are imperfect, right? The atmosphere distorts the light.
And human error creeps into literally every measurement you make.
Exactly.
The source actually mentions Isaac Newton dealing with this.
Huh?
In the year 1700, Newton scribbled down what we now call the normal equations to study the equinoxes.
Wow.
Yeah. He's basically trying to find the mathematical equations that would minimize all those observation errors to find the optimal true path of the celestial bodies.
That makes sense.
And then, in the early 1800s, mathematicians like Legendre and Gauss formalized this into a method called least squares to predict planetary movement.
Right, because they were trying to figure out exactly where a planet would be, even though their telescopes were giving them slightly conflicting readings every single night.
Right.
They were hunting for the true signal hidden within all that noise. But as you mentioned at the start, the term regression didn't actually come from astronomy.
No, it came from Francis Galton in 1886, observing those human heights.
The regression toward mediocrity?
Which, again, sounds so harsh to our modern ears.
It does, but in a statistical sense, it really just meant returning to the center. Today, we call it regression toward the mean.
Right.
Galton plotted the parents' heights against the children's heights, drew a line through the scattered dots to represent that relationship, and the name regression just permanently stuck to the mathematical process of fitting that line.
To ground this in how it actually works, the text gives this really brilliant analogy. Imagine you're throwing a small ball up into the air. If you track its height at various fractions of a second, physics strictly dictates its path.
Right, gravity is pulling it down, the initial velocity is pushing it up.
Exactly. But when you actually measure it, your measurements are going to be slightly off. Your thumb slips on the stopwatch or you blink.
There's always human error.
Yeah. So linear regression is basically a way to estimate those hidden true forces, like the exact initial velocity of the ball, from the messy, imprecise data points we actually observe.
And what's really fascinating here is the fundamental shift in how we view the numbers themselves.
How so?
Well, from a pure mathematical perspective, Your variables, like time and height, are just unknown variables. And the parameters, like the force of gravity, are fixed constants. Gravity isn't changing.
Right.
But from a statistical perspective, which is what regression is, the focus completely flips. Once we substitute our actual observed data for the variables, the model becomes a function of the
Oh, I
parameters.
see.
The parameters become the unknowns that we have to estimate. We are basically using the messy data to work backwards and guess the hidden rules of the game.
We are essentially reverse engineering reality.
Yes, exactly.
Okay, so if we're going to estimate those hidden forces, we need to peek under the hood at the anatomy of this line. The core mechanism doing the heavy lifting here is ordinary least squares, or OLS, and something called the mean squared error.
Right. The basic formula for this is usually written as y equals beta 0 plus beta 1 times x plus epsilon.
Okay, let's apply that formula directly to Galton's family so you can really visualize it. Y is the dependent variable. That's the outcome we want to guess. In this case, the child's height.
Yeah.
We are trying to predict that based on x, our independent variable, which is the parent's height.
And those beta symbols are the parameters. They represent the intercept and the slope of our line.
Right.
They physically define the angle and position of the straight line we're drawing across the graph. But the most crucial part of that entire equation is actually the very last term, epsilon.
Epsilon, the error term.
The noise.
Yeah.
Epsilon acknowledges that our line will literally never be perfect. A child's height isn't purely dictated by their parent's height.
Right. There's a lot of other stuff going on.
Exactly. It captures all the other hidden factors, childhood diet, illness, random genetic mutation, that influence Y but just aren't included in our single X variable.
So the goal of ordinary least squares is to find the specific beta values, the exact line that makes those epsilon errors as small as possible overall.
Yep. And it does that by drawing a line that minimizes the sum of the squared errors. You take the distance from every single messy data point to your proposed perfect line, you square that distance, and you add them all up.
And you want that final number to be as tiny as possible.
Exactly.
But wait, why are we squaring the errors, though? I mean, if we just want the line that is closest to all the dots, why not just measure the absolute distance from the dot to the line and minimize that?
That is a great question. Mathematically, squaring the error does something very specific. It penalizes large errors exponentially more than small errors. Exponentially.
Yeah. If a data point is 1 unit away from your line, the squared error is 1. But if a point is 4 units away, the squared error isn't 4, it's 16.
Wow.
So the model becomes absolutely terrified of being really far off from any single point. It will actively twist and warp the angle of the line just to avoid those massive exponential penalties.
But that seems incredibly vulnerable. Like, what if you have 100 normal data points and one point that is wildly, ridiculously far away?
Like an outlier.
Yeah, like maybe a data entry typo where someone typed a height of 600 inches instead of 60. The model will assign so much importance to that one huge squared error that it will pull the entire regression line away from the true data just to accommodate the typo.
You're exactly right. One bad piece of data can completely derail ordinary least squares.
That's crazy.
The source text actually notes that alternative methods do exist to counter this. There's a technique called least absolute deviation, which does exactly what you suggested earlier. It minimizes the absolute distance without squaring it.
Oh.
Yeah, it's much more robust to massive outliers. But historically, it was computationally harder and just less statistically efficient to calculate by hand, which is why the vulnerable ordinary least squares became the gold standard.
Okay, but if the standard math is this fragile, if one bad data point can warp the whole line, how could statisticians possibly trust it for high-stakes interpretations of reality?
Well, they have to be very careful.
This actually introduces a major theme in our sources, the danger of blind math. Statistics can easily lie to you if you just blindly trust the formula without looking at the real-world context.
Yes.
Take Anscombe's quartet, which is a famous statistical trap mentioned in the text.
Anscombe's quartet is a perfect example. It consists of 4 entirely different data sets.
Yeah.
If you graph them, honestly, a child could tell you they represent 4 different phenomena.
Right.
One is a messy blob of dots. One is a perfect sweeping curve. One is a tight straight line with one massive outlier pulling the math. And one is just a vertical stack of dots with one dot off to the side.
So visually, they literally have nothing in common.
Nothing.
But if you run a simple linear regression on all 4 of those data sets, the math produces the exact same regression line.
Yep.
It outputs the exact same mean. It outputs the same standard deviation, meaning the math calculates that the data spreads out from the average by the exact same amount overall.
It's wild.
And it gives the same correlation coefficient, meaning the formula thinks the variables are moving together in the exact same way across all 4 graphs.
It is the ultimate warning label on the side of the regression box. Always graph your data first.
Always.
Do not just trust the mathematical summary, because the math cannot see the shape of reality. It only sees the numbers you feed it.
Right.
And honestly, the dangers go far beyond visual illusions. There is a major interpretation issue with something called the held-fixed fallacy.
Oh, yeah.
When you move from simple regression to multiple regression, meaning you have many x variables predicting one y, the way you interpret the results gets really tricky.
Right. Let's say you're predicting a house price based on square footage and the number of bedrooms. The standard interpretation of the regression coefficient is, okay, this is the expected change in the price when the square footage changes by 1 unit, while all other variables are held fixed.
Exactly.
The source uses epidemiology to explain why this held fixed concept is necessary. Early studies used observational regression to link tobacco smoking to mortality.
Yes.
If you just regress lifespan against smoking, your results will be skewed by confounding variables. You have to include other variables, like education and income, in the exact same mathematical model.
Because otherwise you're not getting the real picture.
Right. That way, you ensure the shorter lifespan you are seeing is actually isolated to the smoking, and not just reflecting broader socioeconomic factors.
You are trying to find the unique, isolated effect of smoking, mathematically assuming education and income are held fixed in place.
But here's where it gets really interesting. How can you possibly hold a variable fixed in the real world if things naturally move together?
You often can't.
Like using the house example. You can't realistically increase the square footage of a house by 2,000 feet while holding the number of bedrooms fixed at 1. Those two things are deeply correlated in reality.
You've hit on one of the most significant vulnerabilities of multiple regression. It's a problem known as multicollinearity.
Multicollinearity.
Yeah. When predictor variables are strongly correlated in the real world, the mathematical assumption that you can increase one while holding the others perfectly constant becomes a complete fantasy.
Right.
The source text emphasizes that in these highly entangled situations, relying on the individual, isolated effects of a single variable becomes problematic and often entirely meaningless.
So the math will confidently give you a number for what happens when you isolate the variable, but the reality it describes just doesn't actually exist.
Precisely. To solve this, statisticians have to stop looking at isolated variables and instead look at group effects. Instead of asking what happens when one variable changes alone in a vacuum, they have to calculate what happens when the whole group of correlated variables changes together. Because, well, that is how nature actually operates.
The real world doesn't play by isolated rules, and it certainly doesn't always move in straight lines.
Yeah, it doesn't.
Because reality is full of nonlinear relationships, this basic tool actually had to adapt and evolve to survive, which requires clearing up a massive, very common misconception about the word linear.
Oh, this is a big one.
When we say linear regression, everyone pictures a perfectly straight line on a graph. But linear regression doesn't strictly mean the physical shape on the graph has to be a straight line.
Right. It goes back to our earlier distinction between variables and parameters. The model is linear in its unknown parameters, not necessarily in its variables.
Okay, unpack that a bit.
So the beta coefficients, the parameters we are trying to estimate, must be linear. They are only raised to the power of 1. But our x variables, the raw data we feed into the machine, we can transform those however we want before we run the regression.
So we can square the x variable.
Yes.
We can take the logarithm of the x variable. The formula could be y equals beta 0 plus beta 1 times x squared.
Exactly. The x is squared, which physically creates a sweeping curve on your visual graph, but the beta, the parameter of the regression is actually estimating to fit that curve, is still just a simple linear multiplier.
So technically, fitting a curve to data this way is still linear regression.
Yeah. You are fitting a linear model to nonlinear data simply by transforming the inputs.
That's incredibly clever.
And the evolution didn't stop at curves either. The framework expanded into what are called generalized linear models, or GLMs.
GLM.
These were developed for when the real world doesn't give you simple, continuous, easily measurable numbers to predict.
Right, because not everything is a fluid measurement like a price or a height. Sometimes you're counting discrete events.
Like how many people are in a room.
Yeah. The source mentions Poisson regression, which is a type of GLM used for modeling positive quantities that scale wildly, like counting the population of a city or the number of cars passing through an intersection.
Or consider predicting a binary choice like a coin flip, or whether a patient has a specific disease or not. A straight line going off into infinity just doesn't make any sense for a simple yes or no question.
Right.
So statisticians use another GLM called logistic regression.
Okay, but how does that actually map a straight line to a yes or no question?
Well, instead of the line plotting a raw value from 0 to infinity, the math basically bends the output into an S-curve, clamping it so the result is always a percentage between 0 and 1.
Oh, we'll see.
It takes the linear math and translates it into a probability. So a 0.8 output means there is an 80% chance the answer is yes.
Wow. This tool just morphs to fit whatever domain it enters.
It really does.
The real-world applications mentioned in the text are staggering. Like, take building science. There's an ongoing debate over thermal comfort scales for designing HVAC systems.
Oh, yeah, the temperature debate.
Yeah. You ask people in an office to rate how they feel on a scale from -3, which is cold, to +3, which is hot. The debate is entirely about the direction of the regression. Do you regress the comfort votes against the room temperature, treating the temperature as the independent variable? Or do you do the opposite, regressing the temperature against the comfort votes to find the ideal neutral setting?
And deciding which variable is X and which is Y completely changes the mathematical outcome of the model.
Wait, really? Just flipping them?
Yes. If you flip the assumption of what is causing what, you calculate a completely different optimal temperature, which physically changes how the architecture of the building's climate control is calibrated.
That is wild.
Yeah.
And then you have finance.
Mm-hmm.
The capital asset pricing model, the CAPM, uses the beta coefficient of a linear regression to quantify investment risk.
Right.
It measures how much a specific stock jumps around compared to the entire stock market. If a trader sees a stock with a beta of 1, it means the math shows the stock moves perfectly with the market.
Right. It tracks it, exactly.
But if it has a beta of 2, it's twice as volatile. For every 1% the market drops, that stock drops 2%. That single regression coefficient quantifies the exact premium a trader needs to demand for taking on that extra risk.
Wall Street basically runs on this simple mathematical relationship.
And of course, we cannot ignore machine learning.
No, absolutely not. Linear regression is one of the fundamental supervised machine learning algorithms.
So what does this all mean for you listening? It means that before artificial intelligence could generate photorealistic art, or write code, or drive cars, it first had to master the basic act of drawing the best possible line through the noise.
It is the absolute foundation of learning from data. It's the foundational act of taking known inputs and mapped outputs and finding the mathematical bridge between them.
We have covered incredible ground today. We started with 18th century astronomers scribbling equations to track planets, and we followed that exact same mathematical thread. We saw Galton mapping human heights. We navigated the visual traps of Anscombe's quartet. We challenged the illusion of holding variables fixed in a messy world, all the way to the invisible architecture that predicts stock risks and trains modern artificial intelligence.
It's really a testament to the enduring human need to find the signal in the noise.
Definitely.
But I actually want to leave you with a final thought, drawn from an advanced technique mentioned in the text called regularized regression.
Okay.
These are methods like ridge and lasso regression. We talked earlier about how ordinary least squares tries to find the absolutely perfect fit for the data it is given, right? Minimizing that error to 0 if possible.
Yeah, that terrifying penalty for outliers.
Exactly. But sometimes a perfect fit on your past data makes you terrible at predicting the future.
Because it just memorizes all the random noise and outliers instead of learning the actual underlying trend.
Precisely. It's a mathematical failure called overfitting. Your model becomes perfectly adapted to the past and utterly useless for the future. So, regularized regression does something highly counterintuitive. It deliberately introduces mathematical bias into the estimation.
Wait, it intentionally makes its own calculations a little bit wrong on the training data.
Yes, it deliberately accepts a mathematical bias, a slight deviation from the pure data, in order to drastically reduce its variance when it faces brand new, unseen data.
Wow.
It essentially calculates that trying to be absolutely perfect makes the system too fragile. By accepting a little bias, the algorithm becomes vastly more robust and useful when it hits the messy reality of the real world.
The algorithm is literally programmed to abandon perfection to survive.
Exactly. And this raises an important question I want you to mull over.
Okay.
If the most advanced predictive algorithms in the world, the ones managing our finances and driving our cars, are literally programmed to accept a little bit of bias just to function better and survive in reality, What does that say about our own human pursuit of pure, absolute, unbiased truth?
That is a phenomenal question to end on. Because whether you're a 1700s astronomer peering through a foggy telescope or a modern AI crunching millions of data points, you're still just trying to draw a line through a very chaotic reality. Thank you for joining us on this deep dive. We will see you next time.